So,
Okay.
sir, just to brief you about the format, so we'll start at 7:10 sharp once we have enough number of audience, and then I'll give the
Okay.
introduction of today's guest lecture, your introduction, and
Okay.
then you can proceed ahead with the presentation. And post presentation, we'll have a Q&A round if time allows us to.
Okay.
Yeah.
So, mostly, what is the background of the students? Are they engineering students or?
Yeah, all of them are data scientists. Like they are going to be data scientists. They're doing their degree, BS degree in data sciences and applications. So it's a data
Okay,
science background.
data science background. Okay.
All right, we are live, so I think, sir, we can start. Uh,
Okay.
yeah. Good evening to one and all. It is my distinct pleasure to welcome you all to Synapse Talks Episode 2 in collaboration with Escape Group of Corner House. We are honored to have a distinguished guest speaker among us, a visionary scientist, an accomplished engineer, and a leader in the field of space missions and solar projects. Our guest today, Mr. Manish Purohit, is a luminary in the world of space exploration. With an illustrious career as a former ISRO scientist, Mr. Purohit has played a pivotal role in managing critical space missions, including the historic
Recording in
Mangalyaan,
progress.
Chandrayaan 2, and Chandrayaan 3 missions. His expertise extends to the development of solar power systems, where he served as a scientist in the solar panel division of the Power Systems Group at ISRO Satellite Center. Mr. Purohit's passion lies in pushing the boundaries of technology, particularly in the realm of efficiency improvement for photovoltaics and the development of power systems for interplanetary missions, including radioisotope thermoelectric generators. His, contribute, his contributions have not only propelled India's space endeavors, but also have inspired countless individuals in this particular field. Beyond his impressive work at ISRO, Mr. Purohit has continued to make significant contributions. As a testament to his commitment to education and development, he co-founded the National Student Development Forum in Bhilwara. Currently, he is the founder of Nimbus Education, demonstrating his dedication to nurturing the next generation of thinkers and innovators. Explaining the format of today's guest lecture, Manish sir will be presenting a presentation on space technology. Post-presentation, a Q&A session will be carried out where the hosts, that is me, Ayush Khade, and Samriddhi Kashyap will pick the best few questions and iterate them to respected sir, and sir will be answering them. Hence, all the participants, all the students present out there, start dropping your questions in the chat box. You won't be allowed to speak to maintain discipline. So drop your questions in the chat box and we'll try to cover all the relevant questions in the Q&A round at the end if time allows us to. So without further delay, please join me in extending a warm welcome to Mr. Manish Purohit sir. And we are extremely pleased to have you here. Manish sir, all over to you.
Thank you, Synapse and IIT Madras, and hello everyone. So today we are going to talk about three basic aspects of space exploration. We are going to talk about upcoming technologies. We are going to talk about the roadmap that ISRO is going to take up for coming next 20-25 years, because it has already been announced that we want our Indian citizen to be on moon by 2040. So what all has to be done? Where do we stand? And what are the different aspects of technology that we are working on? So today we are going to talk about all that stuff in today's session, right? So let's start with this snapshot. This is the snapshot from the most recent presentation from Somnath sir, Chairman ISRO. And here we can see three streams that are running almost parallel to each other. The first one at the bottommost, from the bottommost left corner, we can see Chandrayaan 3 already accomplished in 2023. And then that particular arrow goes on with SpaceX, Chandrayaan 4, LUPEX, Chandrayaan 5, 6, 7. So like that, we have a series of Chandrayaan missions planned. With that, we have two separate missions, SpaceX and LUPEX. We are going to talk about everything in this particular aspect. Then we have one more stream that starts from human exploration in Earth orbit, which moves in the Gaganyaan, the direction of the Gaganyaan, with humanoid in moon, human in moon, and then moon landing, human moon landing. And if you see the timeline at the bottom, there's a strip. So that goes from 2023 to 2040. Everything has been clearly mentioned here. We have Bharatiya Antariksh Station planned by 2035. Lunar cruise, they are planning for the docking with Artemis Gateway, because Artemis Gateway is going to happen in the Artemis mission of NASA. So all big things are going to happen here, and we are going to discuss everything. The third one is the most important aspect, the launch vehicles, because nothing can be done without a powerful launch vehicle. A suitable launch vehicle is a must for any space endeavor. If you can't beat the gravity of Earth, then that's all. Everything just stays there on the Earth. And if you stay there on the Earth, then there is no space exploration possible. So HLVM3 means human-rated LVM3 are the most successful and the most powerful launch vehicle right now that we have with ISRO is Launch Vehicle Mark 3, 640,000 kgs launch vehicle. And we are going to improve the launch capabilities of this launch vehicle over the period of time. We are going to go towards NGLV, which will be using the semi-cryo engines that are right now under testing and development at the ISRO facilities. And then we have NGLV HR. HR is for human exploration, human rated NGLV. And then we have augmented NGLV, we can see, for a little heavier lift capabilities. So let's start. So if we see, so this is the very first thing. If you talk about the technology aspect, so mostly I want to focus on this thing. You can see here, opto-quantum. So this is what right now ISRO is focusing on, opto-quantum. Not only ISRO, actually, every space agency, or whether it's a private one or a government owned, they want to have a communication setup that is in the field of optical communication with quantum key distribution for better security. And why they are doing that? Because recently we have ISRO as a nation, India as a nation, we have adopted two policies. One is the space policy and other is the quantum mission, with the vision that we will be having fully developed quantum capabilities, quantum computing capabilities with us. So ISRO has already demonstrated quantum key distribution capability over a distance of 300 meters, where they have it has been done by SAC Ahmedabad, the application center of ISRO that is stationed in Ahmedabad. They have developed this thing. So Space Application Center Ahmedabad have done line of sight communication between two campuses that are 300 meters away. So what exactly is QKD and why ISRO wants to do that? Because optical communication can drastically increase the data rates. You can see here 1 Tbps is written here. And if you see here, for Earth observation, we are planning to have real-time video streaming. Means from the satellite, we want to have a real-time video streaming. So such capabilities need higher, better data rates, improved data rates, and then optical communication can for sure provide that higher data rates. So, but it has to go quantum. Why quantum? Because it has to be a more secure one. China is working on that. US is working on that. In recent mission of US, they have sent laser optical communicators on the Psyche mission. Psyche mission is a mission that is going to Psyche 16 asteroid to study the asteroid, and on that mission they have stationed one payload which is going to use laser communication. They are going to communicate with the help of lasers, and if that happens, if that goes successfully well, this means that the data rates that are possible will improve drastically for satellite communication. So now, what exactly ISRO is going to do that? I'm going to cover that quantum key distribution is the very first concept that we are going to cover today. And then we are going to move to the different aspects of the technology that we're going to develop. Okay, fine. So let's start. So quantum cryptography is a term that is very, very relevant when you talk about quantum computers. And quantum cryptography, the most well-known example of quantum cryptography in quantum computers is QKD, quantum key distribution. What happens in quantum key distribution is, when two people, and the best example, the most celebrated example in the world of quantum is Alice and Bob. So when Alice and Bob, they want to communicate with each other, they share a common key. That's a quantum key they share with each other, and they encrypt and decrypt their data with the help of that particular key. And if some third person tries to overhear or eavesdrop, then due to the basic principles of quantum mechanics and quantum physics, he or she, whoever it is, can be easily caught, and it can be easily found out whether someone is listening to that particular information. Now, how that happens? So quantum key distribution is a way to securely share a secret key between two parties. Alice and Bob is a very celebrated example that is used in the world of quantum computing. It uses the principles of quantum mechanics to make it impossible for an eavesdropper, Eve, the name of the eavesdropper is Eve. So when Alice is communicating with the Bob, Eve, when he or she tries to listen to what they are talking about, physics does not allow that to happen. Why? Because there's a basic principle. The principle says that if you try to study the state of quantum system, you break it down. Means, if you have seen that very famous series that came on Albert Einstein, when he talks to Niels Bohr, and when they are talking and crossing the road, and he says that in quantum, if you are not seeing, if you are not looking at it, it's not there, it's everywhere. So Albert Einstein starts crossing the road, and then there's a car approaching, and Niels Bohr says that, "Arey sir, look at the car, it's coming, it might have hit you." So then Albert Einstein said, "But I was not looking at it." So in quantum world, when you are not looking at anything, it can be anywhere, it can be everywhere. And that's what we study when we talk about the clouds, when we talk about the orbitals, the wave nature of electrons in an orbit. And that's what we studied in our class 11th and 12th. Mostly, see, I am talking to the students of IIT Madras, so you all have prepared for your JEE Advanced and JEE Main exam. So you might be very, very clear about that particular idea. So when you talk about dual nature, when you talk about uncertainty principles, Schrodinger's equation, so That's what is quantum physics is. So quantum physics says until unless you're studying any particular quantum system, it can have any possible value. It can be in any state, a probabilistic value. But once you try to capture the value, the measurement you want to take, once you do that measurement, it falls down to that particular value, means you break the system. Now, let's understand this in terms of QKD. So how that happens? So there are two basic principles, two theorems are there. One is no cloning theorem, other is uncertainty principle of physics that helps us in understanding how QKD works. So no cloning theorem says that it is impossible to create a perfect copy of an unknown quantum state. You can't create a perfect copy of an unknown quantum state, because once you try to study the quantum state of any system, you just break it down and it collapses to that particular state, and you break that state of quantum uncertainty. And uncertainty principle says that it is impossible to measure all the possible quantum states with the perfect accuracy. So these are the two principles that are being used in QKD, and how that happens, quickly we'll go through that. So what happens in QKD? Let's say Alice is the QKD transmitter, and on a public channel they are communicating, and Bob is the QKD receiver. On the quantum channel, Alice is sending a key. That key can be, if you see here, that key can be horizontal arrow, vertical arrow, and diagonal arrows. And horizontal O, vertical 1, 0, 1, 0, 1 is given, but you can see here there's a plus sign and there is a cross sign. Cross for the diagonal, plus is for vertical and horizontal. So Alice is sending a particular random number of bits, 1001, 1001, to the Bob. Bob receives it, and then Bob tries to find out the possible key that has been sent by Alice. So Bob tries to match. If they match, then they get the correct. If the measurement matches means, let's say I am Alice and I have used the vertical single photon in the vertical position as 1, horizontal as 0, diagonal as 0, this diagonal as 1, and that's how I have sent it on the channel. But when I'm doing the measurement, I just don't know. Bob doesn't know about what are the keys that Alice has used. So what Bob will do, it will try to randomly use different possible combinations, and some will match, some will not. So if Bob will try to read this particular key with diagonal matrix, it will get a 0, nothing, it will get a false result. If Bob will try to read this particular bit with the help of cross matrix, it will get the correct result. So like that, Bob will get some results of, these are the measurement results. Now these measurement results will be then again communicated back to Alice, and if they match, then the quantum key is being passed to the Bob. Now, if someone tries to listen to this in between, someone tries to capture this quantum key on the quantum channel in between, then the system that will reach to the Bob will be already collapsed. Means it won't be uncertain, it won't be in the quantum state. And once that happens, Bob will get to know that someone has tried to break into that particular stream, break into that particular information channel, and is trying to steal the key. And if that happens, then Bob can ask the Alice to send a new key. And if number of bits that have been sent and that has been tweaked with, tried to break in, are not a very large number. Let's say I'm sending, say here I'm sending something around 8 to 9 bits, and 1 or 2 bits have been tweaked with, touched with, tried to break into it, break into the system. Then there is an upper limit. There's a calculation for that, how much distortion we can allow, because how much distortion has been done by Eve, the eavesdropper, how much it can distort the information that is coming to us. There is an upper limit to that. If we are within that limit, we can continue without any difficulty or without any fear of losing the information. But if our calculation says that the eavesdropper has tried to mend different number of bits more than allowed, then we can ask for a new QKD. And that's what I'm talking about right now. That's what has been done by ISRO over a range of those 300 meters, right? So this is one aspect, quantum key distribution. Actually, I already have done a course on this. It is on my app with the introduction to quantum computing, and you can explore there more, because right now not everything can be explained with the quantum computers here. So you can explore that on the app. Now let's come back to the second aspect. So the second aspect is, let's directly jump towards our upcoming mission. So we will take this particular path. this particular path. Let's talk about this particular path where we have SpaceX, Chandrayaan 4, LUPEX, Chandrayaan 5. So directly, let's see, we have Chandrayaan 4 mission planned. Chandrayaan 4 will happen. If you see here, SpaceX is planned for the 3rd quarter of the next year. Then we have Chandrayaan 4 planned. Then we have LUPEX mission. It is with the JAXA. Then we have Chandrayaan 5. LUPEX mission is a huge one. Why? Because Chandrayaan 3, the recent success that ISRO has seen, and we all have enjoyed that success, the rover was around 26 to 27 kgs. So that rover was in our Vikram lander, and it was around 26 to 27 kgs. In the LUPEX mission, Japan's space agency, JAXA, that's Japan's space agency, they want our lander, Vikram, but their rover is 350 kgs. So right now, the rover that we have sent in Chandrayaan, in Vikram, was 26 kgs. But now we have to design a Vikram lander that can carry a rover of 350 kgs for the JAXA. It's a big mission. We are going to make a mammoth-sized lander for that. So that is LUPEX mission. They are going to explore the lunar surface for different studies they want to do there, in situ experiments they want to do there. So let's start with this. Let's start with Chandrayaan 4. Okay, so this was the first aspect about the quantum key distribution and all. So if you want to ask the questions, you can ask the questions at the end of the session. So what happens in Chandrayaan 4? So there are two possible designs planned, proposed. The one says we will be sending, if you see here, we will be sending one transfer module and one re-entry module on GSLV Mark II, and we are going to send our lander with a sender module. A sender module will be the one that will collect the sample, will lift off from moon surface, come into the orbit, dock with the transfer module, and bring the sample back on Earth. And that will happen with GSLV Mark III or LVM-3, our launch vehicle, which took the Chandrayaan 3. The other proposed plan is we may have a PSLV, which will carry the re-entry module, and I will talk about the details also. And as we took our Chandrayaan 3 in launch vehicle Mark III, same configuration will fly. So we will have a transfer module, a service module, our lander, and our ascender module. So these are the two different possible approaches that have been discussed right now by ISRO. So let's see the first one. So this is a snapshot I have taken from one of the presentation given by Desai sir. He is director of SEC Ahmedabad. He has given this presentation on 17th of November. And here he talks about so many modules and such a plan. So let's go into the details of that. So what he has talked about after Chandrayaan 3, what will happen in Chandrayaan 4? Let's go into the details of that. So as per Desai sir's presentation, the approach for Chandrayaan 4 will be, we will have a re-entry module. Re-entry module will fly with transfer module on GSLV Mark II, and it will go to the GTO. GTO is Geosynchronous Transfer Orbit. Now, what is GTO? So if you remember our Chandrayaan 3, so Chandrayaan 3 was parked in a GTO. Yes. So if you remember these kind of trajectories that have been discussed, so these trajectories, so in Chandrayaan 3, we had these different orbital maneuvers, if you remember. So these are GTO. So we have parked our Chandrayaan 3 in a GTO. Then we did orbit maneuvering. We did those burns. And then on 31st of July 2023, we started our journey towards the moon. We had translunar injection when we started our journey towards the moon. Then after a duration of around 4.5 to 5 days, we were captured by the gravity of the moon. And then we went around the moon, different orbit maneuvers were done. And then on 23rd of August, we had a soft landing. Now, why I have kept these two images side by side? Because this is the Luna 25 that was launched on 11th of August, and that was supposed to land a day before us on the moon. But then, unfortunately, it crash landed. Now, right now, the plan for Chandrayaan 4 is this particular launch vehicle will take the transfer module and service module in this kind of a trajectory. This is GTO trajectory. It will park it in a geosynchronous transfer orbit, and then we'll do the orbit maneuvering. We'll raise the orbit, and then all the duration of those 35 to 40 days are required for our composite module, transfer and re-entry module, to reach the lunar orbit. In the meanwhile, GSLV, LVM3 will take our lander and the ascender module on top of it directly to TLI. What is TLI? So now forget about this Lunar 25. Let's say it's not Lunar 25. This is the trajectory that our Chandrayaan 4 LVM3 is going to follow. What will happen? With the liftoff, directly with the liftoff and the boost that we'll get from our launch vehicle, we are going to put our lander and ascender module in a trajectory that directly moves towards the moon. Now, why we didn't do that in our present case in Chandrayaan 3? Because this particular capability is only possible when we have a very powerful launch vehicle, or the mass that we are carrying is not very huge. So if the mass is not huge, then our launch vehicle can give that kind of a boost, else our launch vehicle has to be very powerful. So when we are just taking our lander and a ascender module, so we can aim for this translunar injection. This means, let's say on that particular day in year 2026, when we are planning our Chandrayaan 4, on 14th of July 2026, our GSLV will take off. GSLV Mark II will lift off from our launch pad in Sriharikota, and it will slowly move in this particular trajectory and go towards the moon. And on 11th of August 2026, our LVM3 will lift off, and it will follow this particular trajectory and go directly towards the moon. And it will take that duration of around 6 to 7 days to reach the moon. And then it will land there, collect the samples, have a liftoff, and come back. But the other plan that has been discussed by Somnath sir, so I have taken this snapshot from the Somnath sir's presentation. Other approach that ISRO is planning to take for Chandrayaan 4 is, we are going to launch our re-entry module on PSLV and the whole composite module on Chandrayaan 4 on LVM3. Now here, if we are going to put extra mass, extra luggage, extra load on our launch vehicle, that means this particular launch vehicle will not be able to do the TLI, translunar injection. So again, let's start that dreaming situation, and we are in year 2026, jump to the future, and it's July 14th, 2026. We have a liftoff, very comfortable one. Our LVM3 has lifted off with Chandrayaan 4 module on board. Now this LVM3 will place our Chandrayaan 4 in GTO. And then again, these all maneuverings will be done, and then it will move towards the moon. So again, it will take around 35 to 42 days to reach the moon, land on the moon. Now, after landing, there has to be something like, sample collection that has to be done. And then that sample will be transferred to the ascender module, and then ascender module has to lift off. Now, how ready we are for these kind of ambitious missions? So, if you talk about the readiness of ISRO, we have already demonstrated soft landing in Chandrayaan 3. I recently have published one article in India Today regarding the same stuff. So we have already demonstrated soft landing aspect of our lander. We are ready to soft land, because we are aiming for the same Shiv Shakti point. Near the Shiv Shakti point only, we are aiming for the landing, soft landing. One thing, we did one hop test on 3rd of September, I think. So on 3rd of September, we did a hop experiment where we reignited the engines on the Vikram lander. Reigniting the engines mean we were able to restart the engines. And when the engines restarted, then we were able to tell that we have the capability to restart our engine and lift off from the lunar surface. So we have demonstrated soft landing aspect. We have demonstrated reignition of the engines. We have already done drilling on the lunar surface, and we have already demonstrated sample in situ, sample collection, and in situ experiment, and reading the values and doing the experiment. This means sample collection for Chandrayaan 4 is not going to be a big issue. So landing aspect has been taken care of. Sample collection, drilling into the lunar regolith will not be a big issue, and reigniting the engines is not going to be a big issue. Then recently our propulsion module has traveled all the way back from the lunar orbit with very calculated orbital maneuvers. We are able to bring it back into the Earth's orbit. So bringing something back from the lunar orbit towards the Earth orbit has already been demonstrated. So if we break down missions like sample return missions, what we are aiming for in Chandrayaan-4, so there are 5 crucial steps that are soft landing, sample collection, and then lifting off from the lunar surface, then orbital docking. That is the main aspect of sample return, orbital docking, then traveling towards the Earth and re-entry. In year 2007, this particular module has already demonstrated re-entry capabilities. We have already demonstrated re-entry capabilities here with the SRE mission. It was SRE mission. It was launched on PSLV launch vehicle. It went to a height of around 650 kilometers in a polar orbit, and then it has made a re-entry into the Earth's atmosphere and safely landed. And we have all the data that was captured during that whole mission. So we have demonstrated re-entry. We have demonstrated re-entry of a crew module also in the CARE mission in 2014. So we have expertise in re-entry. We have done those experiments. Soft landing taken care of. Reigniting the engines for liftoff from the lunar module done. The biggest aspect that remains is docking into the lunar orbit. In-orbit docking. So in-orbit docking is the next mission that we are planning. So ISRO is planning in year 2024 in the 3rd quarter. SpadeX is the name of the mission. So what is going to happen there? And ISRO has already submitted a patent for that docking mechanism, the docking mechanism that has been developed by the in-house team of ISRO. So in the docking mechanism, they have already filed a patent for that design. So what is going to happen there is there are going to be 2 different spacecrafts. One will be the target, other will be the chaser. They will be lifted off from the launch vehicle, within the launch vehicle in an integrated form. Then they will separate out in orbit. They will travel over a distance of few kilometers, and then using the control and guidance, onboard control and guidance, they will track each other down and they will do the in-orbit docking. So that's the SpadeX mission. The full form for the SpadeX will be Space Docking Experiment. That's what ISRO is planning in the next year. So that's what is about Chandrayaan-4, the upcoming mission. So if we go back and look at this particular slide, so once we have the SpadeX in 2024, then we will have Chandrayaan-4 mission in 2026. After that, we are going to go for LUPEX. LUPEX mission, here you can see orbit refueling, RHU fuel cells. So orbit refueling means they are going to try something else also. They are going to try to refuel the spacecraft in orbit. They are trying, if you're running sort of fuel, then ISRO is going to try to do that in orbit. RHU is radioisotope heating units. So I have worked a lot on radioisotope thermoelectric generators. That is kind of a technology that we need when we plan missions like Chandrayaan or missions that go way beyond the Earth's orbit towards the Mars and beyond the Mars, because as we move away from the Earth, we are also moving away from the sun. So solar insolation, the solar radiation, its intensity, it starts falling down drastically. Intensity follows the relation of 1/r². So as the distance increases, intensity falls down in the inverse proportionality of r². The r is the distance from the sun. So as solar intensity falls down, the power generating capabilities of solar cells, solar panels, it also falls down. So either you have to make big panels or you need something else. Now, if we talk about our Chandrayaan-3, there has been a question always asked to me when I went for the media interaction or when I given talks in different institutes, that why our mission was planned just for 14 Earth days, while even Luna was for a bigger duration, Luna 25. Why we were not planning for the bigger duration? Why our missions were not planned for the bigger duration? So the reason being, on moon, sun will be shining for 14 Earth days, and then for the next 14 Earth days, there will be night, very cold, dark, chilling night on moon. So, and we just had solar panels there. We just had solar panels. Now, if you read this thing RHU. RHU is not going to generate any power. RHU is radioisotope heating unit. Right now, ISRO is partnering with Bhabha Atomic Research Center, and they have already proposed a design for heating units and TEGs. TEGs and heating units, they can fly in upcoming missions, but then they need, qualification has to be done for the space applications, and there are different procedures to do that. So radioisotope heating unit will be using a radioisotope material, which will be generating high energy particles, and the energy of those high energy particles will be converted into heat. If it is RTG, radioisotope thermoelectric generator, then that heat will be converted into electrical power, and there's a principle that's called Seebeck effect. So we are going to use that Seebeck effect to convert the difference in temperature into difference in potential, and that's what Seebeck effect is. But right now in RHU, we are not going to generate any electrical power. In RHUs, we are going to use that high energy particles to generate heat. Now, why we need that? Because what happened in Chandrayaan 3 was, once the sun sets on moon, then temperatures, they just take a dip. They go down to very, very, very low values, right? They go down to minus 160, minus 170 degrees. And at that particular low temperatures, even electronics, they hibernate. They go into deep sleep. And what happened? We were trying to wake up our Chandrayaan 3, but it didn't wake up. So that's highly uncertain if we are not having any heating unit with us on board. So that's why we need, if we don't have RTG, at least we should have RHUs, so that they can keep the temperature of that particular box, that heating unit, at that particular temperature, which is required for them to function properly, so that when again the sun rises and it starts generating power with the help of solar panels, then if our electronics is not cryo-cooled, if it is not getting cryo-cooled on the lunar surface, then there is a possibility that we may revive it after those 14 nights on the lunar surface, so that we can extend the duration of the mission. Then it is going to move ahead with Chandrayaan 5. If you see Chandrayaan 5, then it is written there, long mission, RHU and RTEG. So RTEG is radioisotope thermoelectric generator. So once we are going to qualify our RHUs in LUPEX, then Chandrayaan 5 will fly with RHU or RTG. Long mission means then we might be extending the duration of the mission, because still Chandrayaan 4 is still planned for just 14 days. Chandrayaan 4 mission is again the 14-day mission. Chandrayaan 5 might be a longer duration, maybe a month, 2 months, 3 months mission, maybe 100 days kind of a stuff, maybe there. And then we have Chandrayaan 6, Habitat ISRU. So this is something that is related to building a base, setting up the base there, studying different parameters there, because it's a long-term plan. Because if we see here with Chandrayaan 6 here, you can see already Bharatiya Antariksha Station will be coming to the reality. Now let's move ahead. That why all this is happening. If you see this, ISRO is doing so many things: Earth observation, satellite communication, navigation, space science. So many things are happening. See here, it's written ExoWorld mission, Aeronomy missions, space weather, Venus orbiter, Mars landing. So this part comes in our astronomy kind of an explorations, because there has been, see, Aditya. Why we need Aditya mission? Because we want to study the sun. Why? Because sun controls the space weather. If you talk about low Earth orbit, then most of the missions in upcoming future, most of the missions will be focusing on low Earth orbits. If we talk about exploratory part, then we might be going to the moon, we might be going to the Mars, we might be going to the Venus, into the deep space. That is for the exploration, research part. If you talk about the business part, business aspect of the space economy, then most of the stuff will be done from low Earth orbit. Starlink project of SpaceX, thousands of satellites are going to be in the low Earth orbit. Then all those nanosats, CubeSats, they are going to go into the low Earth orbit. Now, Kuiper mission that Jeff Bezos is planning, again the low Earth orbit. OneWeb satellites, low Earth orbit. Global positioning system, low Earth orbit or middle Earth orbit. So this is the point where maximum business lies. Earth observation satellites, remote sensing satellites, means anything that you can extract in the form of a business from the space will be done from the low Earth orbit or the middle Earth orbit segment. So if we are going to place thousands of satellites around the Earth in a low Earth orbit, and then if something is happening on the part of sun, we should be able to predict what's going to happen maybe in 5 to 10 months, maybe next year, or maybe in upcoming 2-3 weeks, or maybe a month ahead. If we get to know what's going to happen to the sun, and we understand the sun, and we have a perfect model of different dynamics that happens in the sun, that's what Aditya is going to do. That's what Aditya is going to help us in understanding different dynamics of the sun. There are so many payloads that are going to study the sun, and we need to do that because we have to model the space weather. Now, why it is important? Let's take a very simple example. Right now, what's happening in Tamil Nadu? We had a very severe cyclone, and then the whole life devastated. And IIT Madras, so Chennai, havoc. Nature has played a havoc there when the cyclone made that it touched the land. Then heavy rains, torrential rains, high speed winds, and flood-like situation. So, but since we knew that there is a low pressure belt in Bay of Bengal, this may happen. So the damage that happened was reduced a bit. But if you're totally unaware, then many lives would have been lost. Many fishermen that might have went into the Bay of Bengal for fishing. So that could have been a very difficult scenario to explain, right? So same thing is expected from these astronomical exploratory missions, these experimental web satellites that we are designing. Even NASA is having so many missions to study about the exoplanets. We have our one ExoWorld mission. We had a payload on Chandrayaan-3, SHAPE payload, that was supposed to study the light that is coming after passing through the Earth's atmosphere, so that we can understand better how spectrum changes, what are the signatures in the spectrum of sunlight or starlight when it passes through a planet which supports life. So these are the things that right now ISRO is doing, taking up. Obviously, ISRO has just started all these missions. ESA has done so many. NASA has done so many. Even right now, there's a mission, Europa Clipper, planned for the next year, which is going to study about the Europa, the moon of the Jupiter, where there is a possibility of life. And then there is a mission called Euclid, which is going to talk about the dark energy and dark matter stuff of the space. So these are the missions that are exploring the universe. And then why I'm talking about all this, because I think that students have to be brought on the same level of understanding about astronomy and astrophysics. And I have announced a course also on that, so you can explore that thing. There's a course on the app, Nimbus Education app. You can explore there. It has already been announced, and I'm going to launch this course on the 3rd week of December. So you can enroll in that course if you are, if you are more interested in such missions. The next astronomy missions are INSIST and Daksh. So you can see here, Daksh twin satellite configuration, each mass 130 kg, 450 power. And they are going to, what Daksh is going to do, they are going to explore about the gravitational wave events. And INSIST is Indian Spectroscopy and Imaging Space Telescope. So it is going to study the stars. So right now, slowly we are taking those steps when we are going to explore the astronomical phenomena of what stars, white dwarfs, and different aspects we are going to explore. And Daksh and ExpoSat, we are going to launch ExpoSat in December, and which ExpoSat is going to search for black hole dynamics. So ExpoSat is there. INSIST is for the stars. Daksh is for gravitational waves. Then ExoWorlds mission. So what the aim of this is, the only aim for ExoWorlds mission is that whether we have those capabilities that we can have a fine guidance sensor, telescope development for exploring the deeper space, sun shield development because we have to protect our payload, our equipments from the incoming solar input. We have to protect our payloads from that. And pointing and stability is very much important. If you talk about pointing and stability, so if you know about James Webb Space Telescope, it is stationed around the Lagrange point, that is away from the Earth, means we are far away from the Earth, means we are far away from the sun. We have taken up that point, and at that point, the James Webb Space Telescope from that point looks into the deep space, and we are going to explore forming of the very first galaxy when it formed, the very first star when it was forming. We want to get that kind of information from the deep space. And there is a big kite-shaped heat shield that, you know, cuts out the infrared radiation or the heat input that is coming from the Earth and the sun. Why? Because those sensors that are there on the James Webb Space Telescope, they have to operate at very low temperatures, 50 Kelvin to 10 Kelvin. And if we are not able to cut out the infrared radiation that are coming from the Earth or the sun, then we are never able to reach that particular low temperatures, what all we may try, because sun is continuously putting in the heat into the surrounding of the solar system. So that kind of a stuff we are going to try in ExoWorlds mission. So this is the aspect about the exploratory part in the astronomy field. So we have talked about ISRO's plan in technology. When we talk about the upcoming technologies, whether it is for the quantum key distribution, for quantum opto communication setups, high bit rates, high data rates, or we talk about the different kind of missions that ISRO is planning, and these all are one of their kind missions which ISRO has never tried, because till date ISRO was more inclined towards those missions that were beneficial for society in the direct way, means remote sensing, then Earth observation, communication. So ISRO was doing most of the missions, almost 100% of all the missions that ISRO has taken up till date were either communication satellites or remote sensing satellites or Earth observation satellites that can have direct impact on the life of common people. But now with the new space policy, 3 different segments have been made in ISRO. One is the ISRO, which is going to take care of, you know, challenging tasks like this, something new, more exploratory work, more research work has to be done. The other one is InSpace, which is going to help the startups to come up, which is going to provide the platform for the startups and build that ecosystem where the new budding talents can be nurtured in the private public partnership kind of stuff. And third one is the Antrix, the other part of the Antrix, that is NSIL. It was previously Antrix. So NSIL is the one that is going to get more, you know, you can say the deals with the private players, launching the satellites, you know, sharing the technology, doing the technology transfer for small satellite launch vehicle, for PSLVs, and getting the private players into the launch capabilities. So these are the 3 different segments that right now the operations of Indian Space Research Organization has been trifurcated, and we are looking for a bigger market. Now, when it comes to the bigger market, means bigger opportunities. So if you continue with these missions, if you explore these missions continuously, you can see that there is a huge possibility for a graduate from physics, for a graduate from software background, for a graduate from mechatronics, mechanical engineering, electrical, electronics, avionics. All the aspects are open. Even astrobiology is the field that is going to boom in the space sector in India in upcoming years with Gaganyaan mission. Fine. So let's move. So the next and the most important aspect is launch vehicles. So let's have a look at this particular slide. We have different launch vehicles here. The very first one is for Gemini, then we have Saturn, then we have Artemis, then we have our LVM-3, then we have Long March, and we have Soyuz. So what is common in all these? The common in all these is there is a pointed nose and some nozzles, small nozzles are coming out. So all these are human flight rated launch vehicles. Either they have taken astronauts or cosmonauts or tachionauts in them, or they are planning to do that. For Artemis and for LVM-3, we are planning it. Artemis is again the second return to the moon mission from the NASA. So they are going to carry the astronauts. So these are called the crew escape modules. Now there's a big difference here. What's the difference here? Difference here is Soyuz has never taken any astronaut. What Soyuz only Saturn is the only launch vehicle that has taken any astronaut to the moon. It has to do that. ISRO has to take the astronauts in the low Earth orbit. Long March of China has taken the astronauts in the low Earth orbit. They have their space station there. Changyong is the name, I think. So they have their already they have the space station there, Chinese space station. So they are frequently carrying their astronauts, the crew, to the low Earth orbit. Soyuz is right now doing the taxi services for NASA, because once the shuttle program was shut down and then they didn't have any other launch vehicle, so Soyuz was doing that. Now you might be saying, but there is SpaceX, there is Blue Origin, Virgin Galactic is there, Boeing is there. They're also trying to do the same stuff. Then why I'm not showing that here? Because they follow a totally different approach. Now you see the difference. So right now, if you see, all these guys are having pointed nose with some nozzles, and all these guys, they don't have pointed nose and you can't see any nozzle, right? This is SpaceX Crew Module, the Dragon capsule that carries the astronauts to the space. This is Boeing's Starliner that is going to get space qualified, and it is going to carry the astronauts. ULA is the United Launch Alliance launch vehicle. So they are going to carry the astronauts in Starliner. And you know about the Blue Origin? It's a space tourism industry which is going to carry the astronauts for space tourism purpose just above the Karaman line, and then bring them back, not to the International Space Station. And this was done by NASA way back when they were exploring the capabilities to lift off with astronauts. Now, there is a difference in both the approaches, but the most important aspect is launching capabilities, how much mass you can carry when you are lifting off. See, if you want to set up a Antriksh station, and if that Antriksh station is somewhere around 23,000 kgs, then your launch vehicle should be able to lift off with 23,000 kgs, right? As simple as that. So let's have a look. So we have our LVM-3 GSLV Mark III. It can carry 8,000 kgs. Our Falcon 9, SpaceX Falcon 9 can carry 22,800 kgs. Falcon Heavy carries 63,800 kgs. Ariane 5, 21,000. Delta 4 Heavy, 28,000. Space Shuttle, 27,500 kgs. That's the comparison to the lifting capabilities, how much mass they can lift to low Earth orbit. Let's say this 8,000 can improve to 10,000 kgs. But right now, this is what the value is. How much we want? Our Bharatiya Antriksh Space Station is going to be somewhere around 20,000 to 23,000 kgs. So this means either we have to increase the capacity, launching capacity, or we have to carry our space station in small segments, and then we have to do the docking, in-orbit docking in the low Earth orbit. Now let's compare. So Falcon Heavy, 63,800 kgs. Now let's see here. Space Shuttle is there. Falcon Heavy is there. There is Long March 9. There is SLS Block 1. Then N1. N1 never flew. Then we have Saturn 5. Saturn 5 was having capability of carrying 140 tons, means 140,000 kgs to low Earth orbit. And it carried humans to the moon. SLS is planning to carry humans to the moon, and it has a capability of 95,000 kgs. It can carry 95,000 kgs to low Earth orbit. This is huge number. Now compare with this number. So we have to cover a lot of ground if we talk about carrying humans to the moon by 2040. The very first and the very most important aspect is launch vehicle. How we are going to beat the gravity of the Earth. So you need a powerful launch vehicle. These are the powerful launch vehicles that are planning to beat the gravity. Long March 9 can carry 140 ton, means 140,000 kgs. Long March 9. Starship Super Heavy can carry 150, yani 150,000 kgs to low Earth orbit, and they are planning to directly go to the Mars. No, it's a huge machine. So if we talk about capacity building, then we need powerful launch vehicles. Now, what makes the launch vehicles powerful? This is the comparison. What makes the launch vehicles powerful? Launch vehicles are made powerful by powerful engines. So if we talk about Saturn V, that carried astronauts to the moon very first time, it had F1 engines. those F1 engines were able to generate the thrust of 7,770 kilonewton, one engine. And there were 5 such engines. So roughly around 33,500 kilonewton of thrust was generated by these are the engines, F1 engines of Saturn V. So Saturn V was, now remember these numbers because we are going to compare the numbers here. So we were getting 35,500 kilonewtons of thrust when we are planning to lift off 140 tons, 140,000 kgs to low Earth orbit. If you want to carry, if you want to take our astronauts to the moon, and if we just follow what they did for Saturn V, we need this much thrust in the stage 1. And the stage 1 was kind of, semi-cryo stage. It was kind of semi-cryo stage, means they were using cryo fuels, and I think it was RP1 or liquid oxygen, like that. Now, most powerful launch vehicle on Earth is Super Heavy booster of Starship. So this Starship, which can carry 150,000 to low Earth orbit, is powered by 33 Raptor engines. Now, each Raptor engine can generate a thrust of 2,000 kilonewton. Now, let's compare. F1 engine can generate a thrust of 7,700 kilonewtons. We just needed 5 for this much thrust. Raptor engine generates, see, 7,000. This is around 2,000. So just, you can say around 3.5 times less, around 2,000 kilonewtons. But then there are 33 Raptor engines. These 33 Raptor engines combined, what we have seen in the Starship Flight Test 2, they generate a huge thrust of 75,000 kilonewtons. So see the difference. The thrust is 33,500 kilonewtons. Capability is 140,000 kgs to the low Earth orbit. Thrust is 75,000 kilonewtons, and capability increases immensely, 150,000. Right, 150,000 kgs to the low Earth orbit, 75,000 kilonewtons of thrust. Now let's compare. We are going to compare these. We are going to compare these. The SLS. SLS is the Artemis. In the Artemis mission, we are going to use SLS launch vehicles. These SLS launch vehicles are going to use RS-25 engines, which can generate 2,000 kilonewton of thrust. We are having 4 such engines. With these 4 such engines, we are not going to get 39,000 kilonewton. How we are going to generate 39,000 kilonewton? So if we go back and see, then in SLS, we have 2 solid boosters. These 2 solid boosters are almost comparable to the solid boosters of our LBM-3. Solid boosters, solid motors, they generate immense thrust. They are the thrust powerhouse. But then there are other limitations to the solid motors. So apart from these 4 RS-25s, we are going to use 2 solid boosters to generate a thrust of 39,000 kilonewton. So 33,500 kilonewton thrust, Saturn V, astronauts on the moon. 75,000 kilonewton of thrust directly going to the Mars. 39,000 kilonewtons of total thrust in the first stage, again planning to take the astronauts on the moon. And then we have, these are the long march engines. China is planning to take astronauts on the moon, their crewed mission, their taikonauts, they call their astronauts taikonauts, they're taikonauts on the moon, and they are going to use this engine. It's a semi-cryo engine with 1,200 kilonewton of thrust. 1,200 kilonewton of thrust. And how much thrust they want to generate in the first stage? 27,000 kilonewton. So roughly we can say they might be using around 25 to 27. So if you see here, if you see closely here, you can see multiple nozzles here. So they are going to, the way SpaceX is using for the Starship Super Heavy booster, so same way clustering is going to happen in Long March also, the China's Long March, which is going to carry the crew to the lunar surface, going to carry their taikonauts to the lunar surface. So they are going to use this semi-cryo engine, and this semi-cryo engine will generate 27,000 kilonewton of thrust. Now, let's compare the thrust of the engines. Now we have this. This is our ISRO semi-cryo engine. How much thrust this can generate? 2000 kilonewton. It's a semi-cryo engine. Semi-cryo engine means RP1 and liquid oxygen. So we are going to use RP1 and liquid oxygen. This semi-cryo engine that is right now under development in ISRO. They are right now calibrating the different aspects of it. We already have the mission sanctioned. The whole project has already been sanctioned by the government of India. The funds have been released, and ISRO is working, overtime to realize this particular engine, this particular machine, because this machine is going to improve our launch capabilities. Now, how this is going to improve? Now, if we compare our semi-cryo with Merlin of SpaceX, it is just 980 kilonewtons. 980 kilonewton Merlin engine, and SpaceX uses Merlin engines in Falcon. They use Merlin engines in Falcon Heavy. In Falcon Heavy, they use 27 Merlin engines. 27 Merlin engines, each Merlin engine 980 kilonewtons of thrust and liftoff capability of 63,800 kgs. But then Falcon Heavy is not space qualified for human flight. They can't carry humans on Falcon Heavy as in the given design, because the vibrational load or acceleration load and different loads that build up, mechanical load that builds up on the astronaut body when it lifts off, is beyond the limits that are allowed for the human rating. So it is not human rated right now. The Falcon Heavy can't carry the crew because it is not human rated. It can carry heavier payloads. It is going to lift off tomorrow early morning around 7 a.m. There is a mission planned. SpaceX is going to carry US Space Force is having a mission of a space plane by Boeing. Something similar to our RLV, reusable launch vehicle. If you have followed ISRO's missions recently, we had RLV, reusable launch vehicle demonstration, in which we have landed our RLV in, we had a liftoff and then it landed on our runway. So we are doing that development of our reusable launch vehicle. It's a space plane. Similarly, there's a space plane from Boeing. X-37B is the name, and 7th flight of X-37B, it's orbital vehicle. So Falcon Heavy is going to carry that particular space plane into the orbit, and then I think they are going to do some maneuvering and going to bring it back and land on the on the runway in their facility, just like space shuttle. So that's the mission planned for tomorrow early morning. I'll try to cover it in a live stream on my channel, on my YouTube channel. I'll be going to do that if everything is good, because there's a 40% probability right now with the weather conditions that there's a 40% clearance for the launch. And if it rains at that time, then there's a possibility that they may scrub it off for the day, right? So if we talk about the launch vehicle engines, so Merlin is having 980 kilonewton of thrust, and we are generating a semi-cryo engine with 2000 kilonewtons of thrust. 2000 kilonewtons of thrust, if we cluster, and I'll just bring that thing here. If we cluster that, so if we cluster those semi-cryo engines, when we cluster those semi-cryo engines, then we can get the required expected launch capabilities. What are our launch capabilities? So if you see here, these are some of the proposed designs for our launch vehicles. So this is our heavy lift vehicle, expendable, semi-cryo 400, semi-cryo 90, cryo 34. Means we are going to do away with our liquid engines. We are going to do away with our solid boosters. We are just going to use semi-cryo and cryo. Semi-cryo will be clustered here, SC400, you can see here, it is in clustered format. So first stage will be having semi-cryo engine, second stage will be having semi-cryo engine, third stage will be having a cryo engine. Right now our cryo engines, they are C25, this is C34, means more capability to carry load, extra load they can carry. They are going to carry extra propellant, and they are going to have extended thrust. Right now the thrust is, they have improved it from 19 to 21 tons. So till now our cryo engines were generating thrust of 19 tons. Now they can generate improved thrust of 21 or 22 tons of thrust they can generate. Means they can carry more propellant and they can carry heavier load, or if they are carrying lighter load, they can carry it for a longer distance. So if we want to carry a payload of 23,000 kgs to low Earth orbit, then this is the proposed design by ISRO, where we are having a central stage of semi-cryo engine. Then we are going to have two other semi-cryo engines as the boosters. Then again, the second stage will be a semi-cryo, and then we are going to have a cryo stage. So this means in future, our liquid engines and solid booster-based engines, ISRO is not going to depend on them much. ISRO is going to develop semi-cryo and cryo stages. Even in the semi-cryo stage and cryo stages, ISRO is planning to use ISROCene, a specific space-grade kerosene developed by ISRO, and they are planning to use Methalox engines. The more greener the fuel is, better ISRO wants to use that for. So they are aiming for the Methalox engines. They are much greener fuels, because the liquid engine that we have, Vikas engine, and the propellant that we use, so that is effectively carcinogenic. That is deadly for humans. So we are going to do away with that. So we are going to build up our launch capabilities with upcoming design upgradations. These are some proposed designs, because we want to have our Bharatiya Antariksh Station. Now, let's spend some 5 to 10 minutes about what possible can be the design of our Bharatiya Antariksh Space Station, our Bharatiya Antariksh Station. See, we are aiming for our 20,000 kg Antariksh Station. So when the Salyut was launched by Roscosmos, Soviets that time, so it had this kind of a design. This is one of the module docked, crew module docked. This is the crew module docked. This is the crew module docked, and this is that space laboratory. And the dimensions, if you see, the mass you see, so it falls in that particular limit. When China first launched their space lab, it was around 8,000 kgs. It was just 8,000 kgs. And then when they got the expertise from 8,000, then they moved to the next, and now they have the full-fledged space station in low Earth orbit. So possibly what may happen is ISRO might be following what Soviets followed. This is the Proton launch vehicle which Soviets have used to launch their space station in the low Earth orbit. It was a single mission to the orbit, where this whole setup was their space station. It was inside this payload fairing on the fourth stage of the launch vehicle, lifted off, placed it into the orbit, and then astronauts were flying, cosmonauts were flying there, and they were staying and they were doing the experiments. Also, the possibility of how many astronauts or cosmonauts that we are going to sustain in our Bharatiya Antariksh Station. So probably right now they are proposing 2 to 3, not more than that, and stays also not for extended duration. Like in International Space Station, astronauts stay 24/7 continuously. Someone is there in the International Space Station, but it won't be that way in our initial design of Bharatiya Antariksh Station. I think they are planning for a shorter duration of, I think, 5 to 6 days, it seems. So gradually the design will improve. But how they can carry in a single stage if the launch vehicle is having the capability to lift off with this much amount of payload. P/L is the payload to the low Earth orbit. 23 ton means 23,000 kgs payload, right? Okay, so this is the comparison right now. This is what we have, and in 2023, LVM-3, and this is what they had in 1980s, which carried their space lab to the orbit. So this is a comparison. These are the few more designs about vertical takeoff and vertical landing launch vehicles of ISRO. In the backdrop, you can see here we have Falcon 9 booster landing on a seaport. So something like that ISRO is also planning. And this is our TVD-1. We recently saw this particular launch vehicle lift off for the Gaganyaan test crew module demonstration. So we had this thing, and ISRO is also planning a space plane with a launch vehicle kind of a stuff, and gradually these details will come out. So like these. So this is space plane from the Boeing that is going to take flight. Space Rider from the ESA. Virgin Galactic is also having that, and we are also planning to have a space plane that is going to lift off. This is going to have totally different applications. It is going to have a payload Bay Area, And mostly applications for space plane right now are towards the army, and for the strategic applications. Mostly it is being discussed that mostly strategic applications will be there. The applications that we are going to use our space plane for will be for the military purposes and all that, and details are going to come later on. Let's see what happens there. But now, so this is again a screenshot from Somnath sir's slide. This is the final slide of his presentation, where we get a very clear idea that what we are aiming for. So we are aiming for a Chandrayaan series in upcoming times: docking, robotics, sample return, long duration missions, in situ resource utilization. We are planning from Chandrayaan 3, 4, 5, 6 series. Then Gaganyaan mission is planned. We want to have our astronauts in orbit in space and bring them back safely on Earth by 2025. Then we have our Bharatiya Antariksh Station planned by 2035. So if we have a look here, this tank kind of a stuff is inflatable habitat that goes in a compressed format, and then it inflates there in orbit. So it is inflatable habitat, this part, in kind of tank kind of a structure that you can see. These are the docking ports where when crew will go, they are going to dock here. And this is evolution of our launch vehicles. So if you see here, this blue and green, this represents the semi-cryo stays, means upcoming launch vehicles of ISRO will be using semi-cryo. And this will be X-34, as we can see here, it has been mentioned here, C-34. So C-34 means better uprated cryo engines will be used, and high thrust semi-cryo engines will be used. We are going to do away with our liquid engines. Solid boosters will still be there. These are the solid boosters. They are still there. These are the Vikas engines that we are going to do away with. Then these are our next generation launch vehicles with the boosters on the side. And these black things you can see here, so they are giving the hint, these black things and these grid fins, they are giving a hint that we are going to design them in a reusable format. These are the landing legs and these are the grid fins. Means this stage is expected to come back and land. This stage is expected to come back and land with the help of grid fins and landing legs. And we can also see grid fins, landing legs here. So what we can make out from these pictures is that ISRO is planning to have vertical takeoff, vertical landing, reusable first stages, uprated engines, semi-cryo engines, because we have to build our capacity. Right now, we don't have launch capabilities that can take our Bharatiya Antariksh Station into the orbit. And to reach there, we need at least 20,000 to 23,000 low Earth orbit launching capabilities. So we need semi-cryo engines and we need clustering of them. But going from that point to liftoff capabilities of 60,000-70,000 kgs to low Earth orbit is again going to be a very big task if we want from 2035 to 2040, we want to take humans to the moon, Indians to the moon effectively. Okay, so that is all from my side. I hope I was able to convey the different aspects on which right now ISRO is involved in and working on. And if you have any questions now, we can have maybe for next 10 to 15 minutes, we can take questions.
Sure, sir. You are amazing. Even I was engrossed in the entire session for an hour. Samrit, you can directly proceed ahead with the questions in the next 10 to 15 minutes, as sir had already conveyed.
Sure. First of all, thank you, sir, for the lecture, and let's move on to the Q&A. So, first question is asked by Nidhi. So she asks, what are the current research trends in the field of QKD, that is quantum key distribution, and are there any upcoming breakthroughs or advancements expected in the QKD technology?
Okay, so see, actually, if you talk about international community, then QKD has been demonstrated over a long range of kilometers range by China for the quantum key distribution. If you talk about quantum computing, and what ISRO has demonstrated till now is up to 300 meters, and we want to increase that thing. So we are going to launch satellites that are going to have a QKD network for quantum key distribution over the range of those different kilometer range, increase the capabilities for having, telecasting the QKD format videos. We can have a video conference that is completely encrypted with the help of QKD. So right now, a lot of things are to be done in the field of QKD. If you talk about different research possibilities that are right now existing in India, so there are a few labs. There is a lab in DRDO, ISRO is working, SEC Ahmedabad is working. Then there is a lab in ISC, there is a lab in RRI, Bengaluru. So these are the institutes that are right now involved in quantum computing and developing these technologies. So you can explore their websites and you can explore their work. And if you wish to work on those particular projects and that particular field, so obviously, after doing your basic, graduation and post-graduation, then if you qualify for that, you can take part on those. You can enroll on those in those institutions and be part of those projects.
All right, sir. So our next question is asked by Mayank Bharti, and he asks that why not use the same technique of changing trajectory slowly, like of Chandrayaan 3 for Chandrayaan 4, as it will carry a mammoth size of lander and rover. So is ISRO planning to do something different, because this is not a hit or try kind of mission?
Okay, so if we go back there and see, then I have talked about both the two designs. If you see here, one of the design talks about this approach talks about the same stuff, what you are talking about here. So we are going to park our composite module in the GTO, and then gradually we are going to raise the orbit and do the TLI. But if we are going to use this particular approach, then since the load will be lesser, so we can directly aim for TLI. Because see, it is defined by the capabilities of your launch vehicle. If you have a powerful launch vehicle, then you are never going to do this maneuvering, because it takes time. Okay, we have mastered the art of orbital raising and orbital maneuvering, but then staying such a long duration in space, going in orbit, you have to be very lucky that nothing goes wrong. You have to be very lucky for that, because there are so many subsystems, there are so many sensors are working, there are so many operations that are happening. So you have to be very, very lucky that nothing goes wrong, and we have been very lucky. So shorter the duration of this journey and directly reaching the destination earlier, it's always preferred. So yes, we can have both the approaches. The better one is, if you have a powerful launch vehicle, the better one is going directly to the moon.
Got it, sir. So next question, it is asked by Ashutosh Kashyap, and he asked that Elon Musk envisions a self-sustaining city on Mars within a few 20 years. So what preparations have been made for that, or is it a vision more of a speech stunt? And how do you see this ambitious vision? Like, is it just a stunt that he made in the Cybertruck launch event?
No, actually, see, someone has to make ambitious. Someone has to take ambitious steps. Have to set ambitious goals. Let's go back in 1950s and 1960s. It's not like that US or USSR, they were not exploring the possibilities of space and using the space for totally different purpose. They were aiming to use the space for, for military and different purposes they were aiming, because that was a Cold War era. But then with the launch of Sputnik and then the first person in space by Soviets, the whole new thing started, going to the moon. At that time, same thing might have been asked, that is it possible to go to the moon? It's so far away, no atmosphere, nothing, we know nothing about the moon. But then we have sent people to the moon, we have sent astronauts to the moon, and they have stayed there, and we had so many missions. And then that part happened. And when that happened, the technology developed. So you have to be a bit ambitious. If we go back and talk about having technologies that right now we have in this present day, if you talk about those technologies 50, 60 years back, then again, the question comes the same way. Is it really possible? It is really feasible? So until unless we challenge ourselves, how we are going to see the technology development? So it's more kind of a challenge. It's an ambitious challenge that has been set forth. whether it is a car named Tesla that drives itself and takes care of everything, super powerful, super robust, and very safe, or it's a Starship kind of a launch vehicle that is super powerful, having super powerful liftoff capabilities. So once we challenge ourselves, then only technology nurtures. So it's good.
Yes, so like in 1950s, John F. Kennedy, he just asked uh his all his citizens that why can't we set high standards for ourselves? And in next 10 years,
Yeah.
they were on
See,
moon.
the legend has it that that thing was, the president was convinced for such kind of a mission based on a novel. So, how ambitious that was. So sometimes we have to, you have to do something out of the league to be out of the league.
Yes, sir.
Mm.
So also one of our students, wait a minute. Yes, so what is the future of electric propulsion? This is asked by
Mhm.
Tejas. So
Mhm.
what is the future, or would we be transitioning to or we are looking to other fuels, like as you talked about methyl and all?
Okay, Psyche mission of NASA that is going to travel somewhere around 2.2 billion miles of distance is totally dependent on electronic propulsion. They are going to use xenon ions, xenon ion thrusters, Hall effect thrusters they are using for the propulsion system. So when we are in space, when gravity is not much of an issue, then uh, ion thrusters are more efficient than any of our launch vehicle engines. So it is already there. So huge, future is huge for them. So once we are out of the gravity of Earth, then it's one of the best way to use because ion thrusters are more efficient in terms of covering the distance and amount of money you spend on the fuel and amount of time. So efficiency in terms of both money and time and performance. It's good. And it's happening. Even in India, there are startups that are working on ion thrusters. So that is the next thing that is going to happen. See, if you have ion thrusters on board, then for housekeeping, orbital housekeeping, for maintaining the orientation of the spacecraft and doing some maneuvering in orbit, it becomes easy. So it's really good. Once this technology matures, so we are going to see it more often flying on the spacecrafts. Initially, for liftoff, we need semi-cryo or cryo because we need huge thrust. Right now, ion thrusters, they can't generate that kind of a huge thrust. No, they can't generate. They generate a very feeble thrust. But since when we are not in gravity space, we are out of the gravity of Earth and we are just falling freely somewhere in the space, then even that thrust can carry you to the places. As it is going to carry the Psyche to the Psyche 16 asteroid belt. So it is going to carry the Psyche mission to the Psyche 16, which is going to reach there in, I think, 2029, covering the distance of around 2.2 billion miles, I think, if I'm not wrong.
Got it. So since you mentioned startups in your previous answer, I would like to ask what are the domains that the startups want to collaborate, which want to collaborate with ISRO should focus on? This is being asked by Parth.
So actually, right now, even I am working on an idea. So to be very clear, and to all the friends right now who are listening to me, even in the most recent presentation by ISRO, the startup ecosystem that is going to develop in India or in the space economy will be mostly focusing on the service segment. If we break down the complete space economy, let's say right now the space economy stands at somewhere around 500 billion USDs. So that 500 billion USD market, and right now our share, ISRO's, India's share in that market is somewhere around 2 to 3%. And we want to capture, I think, 9% by 2030. That's why Government of India wants more startups to come in. if you look at the pie chart of that particular space economy, that where the maximum opportunities lie, so 10%, around 10% is the launch vehicle segment, that launch facilities and launch services. That is just 10% of the complete space economy. More than 50% will be the service segment. Service segment means you launch a satellite, so you have a launch vehicle, you have a manufacturing facilities where you manufacture satellites, you do it on order, or maybe you have your in-house capabilities. Then the data that you are generating, once you are observing the Earth, whether it's an Earth observation satellite or it's a nanosat, CubeSat. So one of my idea has already been selected by Government of India, and we are working on that. It is regarding the CubeSat designs. And one of the startup that I am right now engaged in with different youths, different young minds, is regarding the service segment, where we are going to take up the data that is generated by the spacecraft that observes the Earth. Let's say upcoming mission of NASA and ISRO, NISAR, if you have heard the name, NISAR, that is NASA ISRO Synthetic Aperture Radar. So that particular spacecraft is going to capture whole of the Earth in 12 days. Means you have a data set for complete Earth, everything covered in 12 days, and then it refreshes the data in the upcoming 12 days. That data can be used for multiple purposes, for city planning, management, for fleet management, for weather forecasting, real-time weather forecasting, for agricultural purposes. So many applications. So if you are planning to venture into the startup segment in the space sector, then you should be ready with your coding skills. You should be ready with your machine learning skills or artificial intelligence coding skills. You should have a good command on those particular coding languages that can help you in doing that. Then start exploring the data sets that are available right now. NASA is providing some data sets. ISRO provides data sets on Bhunidhi website. Go explore that and see how you can parse that data. What is the possible information that you can bring it out from that data set, how you can read the data set, and how you can do the value addition. Because if more than 50% market will be captured by this particular segment that is going to capture the data and convert it into a relevant information. And that's what we call service segment.
Got it, sir. So those points should be kept in mind while we are planning to collaborate with ISRO. So, speaking of lunar exploration, given the recent strides in the field, where do you envision the most significant leaps or breakthroughs occurring over the next decade?
With respect to ISRO or with respect to the global community? With respect to the global
Global
community,
community.
then Artemis will be setting up a space station, lunar space station around the moon in a lunar orbit, and they are going to set up a base camp on the moon, exploring the possibilities of water, and then using that particular base camp to jump towards the interplanetary missions. So this has already been planned, and next decade, let's talk about 2030s till 2040. So we will be seeing that thing happening in reality. Artemis is planned for 2028-29, where they are going to land the astronauts on the moon again. Now this time they are going to go to the southern polar region, and they are going to explore the polar region. They are going to set up a gateway, that is the lunar space station in an orbit around the moon, which is going to be used as a gateway for interplanetary missions. You can dock with the lunar space station just the way we do with the International Space Station. Astronauts fly from Earth, go to the International Space Station, and then they again back on Earth. Same way, astronauts are going to fly from the Earth, go to the lunar space station, dock there, go to the lunar surface, do the experiments, again come back, dock with the lunar space station. If you see in the presentation, we have that thing here. We have a plan of lunar cruiser docking with Artemis Gateway. Artemis gateway is that lunar gateway that Artemis is planning in the lunar orbit. So what that going to help us in? So the going to the moon is going to become very easy for us. So then we don't have to have, that huge launch capabilities are not required. We can use our lunar cruisers, dock with the lunar gateway, and then from there take a journey of landing on the lunar surface. Once you have to refuel yourself, and once your supplies are out of, in the shortage, then again the supplies can come from Earth. And if you want to go on a journey to the interstellar space, then take the journey onwards for interplanetary missions. So that's going to happen. It will become a reality in next decade for sure.
Got it, sir. So due to the shortage of time, I cannot ask you more questions. And I want to personally express that how much we all have enjoyed your session and your insights on India's space scene. It was truly fascinating and impressive. And your insights, they truly gave me a whole new perspective and made us pretty much more hopeful about India's future in the space game. And thanks a lot for sharing your knowledge and making it such an informative session.
Thank you everyone in present here, and I'm really happy to interact with you guys. And if you want to connect with me, then I'm available on all the social media handles. I am on LinkedIn, I am on Twitter, I am on Insta. I have a YouTube channel named Nimbus Education. So if in case you have any queries, you can drop me a message there, and for sure I'm going to respond for that. Don't worry about that. So stay connected, and I hope you all enjoyed the session. And thank you, IIT Madras Synapse, for giving me this opportunity to interact with the students. Thank you.
Thank you so much, sir. I have already dropped down the link of all the required channels and your app as well in the chat section. So I hope students will be able to connect with you. So concluding the guest lecture, as we come to the end of this insightful and thought-provoking guest lecture, I would like to express my sincerest gratitude and appreciation to our esteemed speaker, Manish Purohit, sir, for sharing his expertise and knowledge with us today. His unique perspectives and enlightening insights have enriched our understanding and opened up new horizons in the field of space technology. As I have already said multiple times, do not forget to follow Nimbus Education and on YouTube and other social media platforms to learn more from Manish sir. The links have dropped down multiple times, and the links will be shared in the WhatsApp group and via mail as well. You don't have to worry. Thank you, Manish sir, and thank you everyone for joining in. Have a good night. I'll be ending the guest lecture with Manish sir's permission.
Okay, sure. Thank you everyone. Thank you.
Thank you so much, sir. Thank you everyone for joining in. Have a good night.